And now we revisit this example of a subspace. This is a specific example we had previously worked with. This is a specific subspace of M sub 2, 2. These are 2 by 2 matrices such that the entries of those matrices satisfy these two equations, and we consider A, B, C, and D as unknowns or variables. By satisfying these equations, what we're saying is that this is a homogeneous system of equations, which also transforms or is equivalent into stating membership on the null space of this matrix that we specify here. This is a 2 by 4, a matrix that is 2 by 4, and membership on the null space of this 2 by 4 matrix is essentially those entries that are members of the null space of this 2 by 4, those entries would be the entries that define a matrix that's a member of this set Z, which is a subspace of M sub 2, 2. So we review or revisit this example. We do the following. We consider this 2 by 4 matrix and observe that the reduced row echelon form of that 2 by 4 matrix is this, right? So what we have is that this matrix with columns 1, minus 2, 3, minus 6, minus 1, 3, minus 5, 4, 0, 0. We augment that by the column of zeros in the scenario where we're considering null space or a solution of the homogeneous system. That row reduces to a matrix that looks like this, and this implies, right, in this case we have that columns 1 and 3, here we have that the set D is 1 and 3, columns 1 and 3 are the columns with pivots, with leading ones, and we would classify variables 2 and 4 as the free variables, right? So here variable 2 and 4, we're saying the set F here contains 2, 4, and 5, but are the variables 2 and position 4, those are the variables that are considered the free variables, and therefore we would consider A and C as the dependent variables. This is to say that we could express A, for example, A could be expressed as minus 3B plus 1 plus 1D, and we could also express C as minus 4D, right? So we can make these substitutions because A and C are the dependent variables, and we can substitute A and C by expressions in terms of the free variables. And so that leads, this is a slide that we had worked out with before, that leads to making substitutions on the definition of this set. We can substitute for the expressions substitute for the expressions A and C, and these expressions are substituted precisely by the expressions that we obtain from the row reduction. So on the entries 1, 1, and 2, 1, we can then write expressions in terms of B and D, the free variables, and by doing so, we can express this 2 by 2 matrix, as the sum of two matrices, each of them also 2 rows and 2 columns, such that the first matrix is all in terms of B. You can think of this as 0B and 0B on the second row, and the other matrix also in terms of the other free variables. You can think of this as 0D, which means that we have B times this matrix minus 3, 0, 1, 0, and D times the matrix 1 minus 4, 0, 1. And since B and D are free variables, then this linear combination is denoting that this set Z is the span of this matrix and the span of the set that contains this matrix and that matrix. In other words, Z can be represented, C can be represented as the span of some set, okay? And that set is what we denote here by the set Q. Q denotes the set with these two matrices, and basically by relying on techniques about calculation of null space, we have been able to express the given set Z as the span of Q, or as a linear combination of these two matrices. So we can phrase this property as the following. We can say Q is a spanning set. Specifically, Q is a spanning set for the subspace Z, the subspace of M22, defined by matrices whose entries satisfy these equations, considered a homogeneous system of equations. And so Q is a set that has the spanning property. But so it remains for us to address, is this set Q a basis? And to really answer that question of whether or not Q is a basis, then we need to address linear independence. Linear independence is addressed by writing a relation of linear dependence, which in this case would look like 0 equal to the linear combination alpha 1 and alpha 2 are scalars, linear combination of elements of the set we are trying to determine whether or not those members of that set are linearly independent, and we translate this linear combination into equating, this is a matrix equation, the 0 matrix, with this 2 by 2 matrix, and by doing so, comparing entry by entry, we obtain a set of equations, consider also a homogeneous system of equations, but we could form the matrix, augmented matrix, and compute the solutions for this homogeneous system, but also we observe each of these equations resolve by comparing entry here 1, 1 with entry 1, 1. That gives you the first equation and so on. But we observe that it comes out that alpha 1 and alpha 2 are 0, and then this is a system of equations that is consistent with the having a solution as the trivial solution, which implies that this is in fact the only solution of this homogeneous system, and that implies linear independence. In other words, we conclude that Q is linearly independent, and since we had already established that Q is a spanning set, then we would rule that Q is indeed a basis for that subspace.